So I don't know whether it's worth to speak right before lunch or right after lunch, but anyway, I'm glad everybody finally got something to eat. So yes, I'm going to talk about xenotransplantation. I have some disclosures that are here. The ones that are in bold are relevant to this talk. So this is going to be, a little bit xenotransplant light, because I don't want to lose people in a lot of technical mumbo jumbo. So we won't go too deeply into the science. Now, I just want to warn everyone that there are some pictures of organs and things like that. And I will give you a little warning, right before I show any of them. And if you're disturbed by that or anything, you might want to close your eyes, or if you just want to skip this lecture, that's fine too. It's not anything too bad. And the one that probably might be the most difficult I removed. So, all right. So we've sort of been through the inconvenient truths and revelations, I think, earlier, but I'll just point out one, which I'm not sure whether it's been said or not, but the ceiling on organ donation really comes from the fact that way less than 1% of the people who die every year die in a manner where they could become a donor. Okay, and that's probably not going to change. And unfortunately, despite a lot of innovation and things like paired donation, we have not made headway in living donation in the last decade and a half. Very little bit the last year or two, but it's really remained pretty flat. And that's been a bit disappointing. And so, you hear a lot about different incremental improvements in our system and some, audacious ideas about changing certain things. And all of those things are important to consider. And the people who are working on those things, are doing great stuff. We do, in the US now have a donation rate that equals that of Spain, which a lot of people don't realize. And I guess I would make the argument that, these various strategies that people are thinking about redoing our system of allocation and oversight, reducing discards, presumed consent, incentives, paying donors. All these things are interesting ideas, and every organ that goes into another human is important. But if you could just wave a wand right now and change all of these things tomorrow, we still wouldn't have enough organs. So, I really feel that we're at a point where we have to identify another source of organs. In fact, we're way beyond that point. And I think the two most promising technologies that could produce an unlimited sustainable supply of organs are bioartificial organs. So organs that are basically created in the laboratory by placing stem cells on some type of scaffolding, either an artificial scaffolding or a decellularized matrix from a pig organ, and then coaxing those stem cells down different pathways to recreate an organ. Now, obviously, it's a lot harder to start from scratch when you're building an organ than to take an organ that already exists and try to make it more compatible with humans. And that's really the idea of xenotransplantation. And the species that we've decided upon over many years of debating this and thinking about this and trying other things is the pig, for better or for worse. And their organs are about the same size as humans. And if you can introduce your gene edits to make them more acceptable to the human immune system, or to produce the physiologic responses that are going to be necessary to recapitulate the function of a human organ, And do that in a way where you can breed that into a pig herd. You could scale this up pretty well. One of the problems is that, and I'll talk about some complicated gene edits, that the more complicated they are, the less likely they are to be able to be bred, and the more likely they are to need to be cloned one pig at a time. And that's a big deal. And so we're trying to solve a crisis of organ availability, and we don't want to do that with an equally scarce animal substitution. So that's one thing to keep in mind. But I think about these two bioartificial organs and xenotransplantation as sort of the sun, the solar and the wind of the future of organ supply. So what is the big challenge in taking a pig organ and transplanting it into a human? On the left side is an example of an organ that is being hyperacutely rejected. So it turns that purple color almost immediately right after the blood flows into the organ from the human blood vessels that it's attached to. And in the case of xenotransplantation, what causes that is primarily one antibody against one carbohydrate. And that carbohydrate is called alpha-gal. And that carbohydrate was lost during evolution from pigs to humans. And believe it or not, 1% of our total antibodies are directed against that carbohydrate. So why would that be? Well, we think it's because that the antigens, or the things that antibodies recognize in bacteria, on the surface of bacteria, share a commonality with the alpha-gal carbohydrate. And so it's in our best interest to keep our bacteria in our colon. And so we have this very vigorous response against this sugar, this carbohydrate. And the kidney on the right side has been modified to remove that carbohydrate. So the human that receives that kidney still has all of those antibodies, but there's no target for the antibodies because you've removed that carbohydrate. And pigs do just fine without that carbohydrate, by the way. There are two other carbohydrates. One's called SEMA, the other beta-4-gal, that are also have been lost, and we have pseudogenes to these the enzymes that make these carbohydrates, and we have some level of antibody, but much smaller. About 90% of our preformed antibody, and everybody in this room has these antibodies. There's varying degrees of how much you have, but everybody has it. And that probably develops immediately after birth. And so about 90% of your antibodies are probably against alpha-gal, and then SEMA and beta-4-gal make up maybe 6%, and then there's some that we have no idea what they are against. Now, we and others, came up with this concept of testing xenografts in people who were brain dead, who had wanted and intended to donate their organs, but for whatever reason, those organs weren't suitable for donation. And so we approached their families to ask essentially for whole body donation for the purposes of some high stakes breakthrough innovation. In this case, to test a xenograft, but it probably won't be limited to that moving into the future. So you'll probably see we refer to these brain dead individuals whose hearts are still beating and they're on a ventilator, but they've been declared dead. We refer to them as decedents, and you'll probably see decedents involved in other kind of breakthrough technologies, I would think, moving forward. So it's probably not just limited to transplantation. And so we, feel that this is a way to de-risk what we call phase 1, phase 2 trials, which are safety trials, okay? And I've listed here some examples of some of these safety trials that have gone badly wrong, okay? And one that you may remember is Jesse Geisinger, who received one of the earliest gene therapy protocols and died from that. And it really set gene therapy back about 20 years. We're just now starting to see gene therapy protocols being reintroduced in the last 4 or 5 years. But it really had a huge impact. One that had a big impact, I was at Hopkins when this happened, was Ellen Roche, who was a healthy volunteer who actually worked for the primary investigator in this trial, this asthma trial. And she died, and it shut down all of our protocols and IRB studies at Hopkins for a pretty long period of time. I had several desensitization trials that were shut down while they tried to really understand what had happened here. And then I list another example of a drug that was designed to interact with a molecule called CD28, which caused multi-organ system failure in 6 healthy volunteers because there was a significant species difference between CD28 on animal cells versus human cells. And so there was no way to predict that really until they did those first human trials. And so again, one great advantage of testing some of these things in humans, in brain dead humans or decedents, is that some of these things might not have happened. And, there's a lot of concern with xenotransplantation, rightfully so, about another pandemic and the possibility of some type of pathogen from a pig being transmitted into a human. Now, those of us who've been in this field for a long time feel that this risk is extremely small, but still it's a concern. And so one of the things that I think we've been able to do with the decedent model is to test. There's been about, I would say we're probably up to about 8 or 9 organs, xeno organs that have been tested in decedents. And, we've carefully monitored for all of these pathogens. And there's only been one case, which was actually from the University of Maryland, where there was a reactivation of a virus, porcine endogenous, porcine CMV, cytomegalovirus, which did not infect any human cells, but it did get reactivated in the heart and may have contributed to that heart failing. So, we're very concerned about this and vigilant and doing very intensive surveillance. But, so far things have looked quite good. And again, I think, in the idea of being able to fail safe in decedents, it's a good way to test these organs initially. And that, then this new model allowed us to move a gene-edited pig kidney into a human for the first time in September of 2021. And we also got a good sense for what the public reaction to this was going to be from this transplant that we did 3 years ago. And this is that first kidney, and we attached it. So sorry, I didn't give you a warning, but so this is a pig kidney that's attached to the blood vessels in the upper thigh of this decedent. And we did it this way because we only had permission at the time to study it for 3 days. So we could do frequent biopsies, and we could also look at the kidney and see that nice pink color and know that it was well perfused. It wasn't being rejected. And that turned out, that experiment, very good. We then moved on after doing another kidney to do 2 heart transplants. These are pig hearts beating in the chest of 2 brain dead humans. And again, we were able to observe these hearts and do various tests for 3 days. And you can see the echocardiograms on the right side. Now, those 2 kidneys that we transplanted were the alpha-gal knockout, that 1 carbohydrate. And then I'll talk to you a little bit about the other thing that we did, which sort of is in alignment with what Dr. Newell was talking about, which was we transplanted the thymus from the pig underneath the capsule of those kidneys. And I'll show you that in a few minutes. This heart actually was a 10 gene edited heart. So it had those 3 carbohydrates that I mentioned knocked out. Plus it had a knockout of the growth hormone receptor. And the reason why is these are outbred pigs, and the hearts are removed at about 8 months, but you know, those pigs will go on to grow and become much larger than humans. And because the heart is, you know, in a position between the sternum and the backbone, there was a concern that it could get compressed as if it did continue to increase in size. So by knocking out that growth hormone receptor, you could control the size of the heart. And then we introduced 6 human transgenes into the pig genome. The company that makes these pigs did. And these human copies of important regulatory proteins in certain pathways that we know can be problematic in compatibility between pig and human. And those pathways are these major systemic pathways like coagulation, so blood clotting, like inflammation, and something called the complement system, which is important to the immune response. So when you hear about these gene edits, that's really what we're talking about. Knockouts, so removing, you know, the carbohydrate or the protein, or knock-ins, introducing a human copy into the genome of the pig, of the organ that you're transplanting. Now, this was an alpha-gal knockout pig kidney, and you can see right up here, this little triangle, that is the thymus of the pig that was placed underneath the capsule of the kidney 2 months before we procured that kidney. And it has good vascular supply when you put it there. And again, the idea there is that the thymus is the organ that tells the immune system early in life what it should respond to and what it shouldn't respond to, right? And so it educates the immune system. And so we're trying to re-educate the immune system in that thymus to not recognize the pig tissue as being foreign. And that's the whole idea behind this. And this is all based on work that was done at Columbia. And I'll tell you a little bit about that in a minute. So in this case, we got permission to study one of these pig kidneys, the alpha-gal knockout thymo kidney, in a decedent for 2 months. So we could really see what was happening in the immune response and also the physiology of the kidney. Can it do everything that a human kidney can do? And so I just want to point out that we use all standard immunosuppression, nothing experimental, but pretty heavy immunosuppression. And the hope of that transplanting that thymus is that we could start to reduce that immunosuppression if we got some level of tolerance after these transplants. And indeed, at 1 month, we did get sort of the classic findings of a rejection, in this case, an antibody-mediated rejection. And the good news was the kidney was working great, had a creatinine of 0.3. We all would want to have that. Up until that rejection, it went up to 0.7 then, which is actually a significant change. And the good news is we were able to treat this rejection for the first time in a xenograft using standard things, standard therapies that we use to treat rejection in human organs. And it completely resolved. And when we took that kidney out, you can see it on the right side there. It looked absolutely normal, was normal size. And we had to take it out at 2 months because that's what we had permission to do and return the body to the family. And when we took the kidney out, it had a creatinine of 0.2 and, obviously was functioning very well. Now, there have been a total of 4 xenotransplants that have been done in living humans. So everything I've shown you up to this point have been in decedents, right? And you probably remember the 2 hearts that were done first at the University of Maryland. And both of those patients who were really severely ill, they had no other chance of living, no other options. They weren't candidates for transplantation. And again, they were extremely ill. They both died in less than 2 months and both had antibody-mediated rejection at the time of their death. And so this was a shorter period of time than would have been predicted from the primate studies that were presented to the FDA as proof that they could possibly get up to a year of good function in these hearts. And then there was the eGenesis 69 gene edited kidney that was done at Mass General. And that patient had a sudden death about 6 weeks after the transplant, had a functioning kidney without rejection at the time of that sudden death. We don't know exactly what that was from, but there was some evidence that it could have been a heart attack. And there was an early, what we call cellular rejection, so the other type of rejection that was successfully treated in that patient. And then we performed a living donor combination of what's called an LVAD, which is a heart pump in a patient who had heart failure and kidney failure, was not a candidate for a heart kidney transplant, was not a candidate for an LVAD actually as what we call destination therapy to try to make her feel better and live longer because she was on dialysis. And patients who get an LVAD on dialysis do extremely poorly. And so we went to the FDA based on the decedent work that we had done and were given the opportunity to help to save this patient's life, who was extremely ill. In fact, she arrested the first night she came into the hospital before we did the LVAD and the kidney transplant. And we learned quite a lot, but in the end, the LVAD, which worked well for the first month, and she had a creatinine of 0.5 to 0.7. When she developed a blood infection and her blood vessels dilated, the LVAD couldn't really keep up with that challenge, and the kidney developed an ischemic type of injury, and we had to remove it at 47 days. So this is that operation, and you can see over here this nice pink kidney right after reperfusion. We put that kidney in about a week after we placed the LVAD. And, Lisa Pisano gave many interviews and was well known to the media and to people who, were following her story. And that's her a couple of weeks after the transplant, texting and Zooming with her family. And, again, this kidney that she received was an alpha-gal knockout. And you can see this is the thymus underneath the capsule of the kidney. That's kidney tissue right there. And the amazing thing is that in order to get this thymus under the capsule of the kidney, we actually mince it up into tiny little pieces. And then somehow magically, during those 2 months when it's sitting inside the pig, it reforms a completely normal thymus. And nobody really knows how that happens. But anyway, so she again received, a pretty much more significant level of immunosuppression than those of us in this room who have had transplants, because, again, we're transplanting between two different species. But I think Lisa's legacy, which is going to be really significant, is that we saw evidence. So we removed the kidney at 47 days. And the folks at Columbia, David Sachs, who really came up with this idea of transplanting the thymus and pioneered all of this, and Megan Sykes, looked at the thymus, in the kidney that we took out, and found that it was supporting that process of re-educating the human cells from Lisa. And when we tested her cells against her donor pig, they didn't respond. But they did respond against another pig, and they did respond against another human. So showing that they could have responded, but they specifically were tolerized to the donor pig. So this is very exciting, and we're going to report this shortly. But I think this gives a tremendous amount of hope for the future, that maybe in these xenotransplants, we could start to reduce some of this immunosuppression that we have to give to get these things to work, for the first month or two. And we're, I think what you're going to see in 2025 is a couple of phase 1, phase 2 clinical trials, several of them probably. And we're excited to partner with our colleagues at Columbia on one of those trials. So we're really looking forward to that. So it's going to be very exciting. And that's what I have. Lots of people involved in this work. But, first and foremost, I just want to acknowledge the families of our decedents who really allowed this thing to move forward, because we've been, in doing these xenotransplants in primates for 20 or 30 years without a clear pathway into humans. And they took this leap with us, something they had never heard of, something that had never been done before, and allowed their loved one to participate in this. And thank you very much for your attention.